Good evening, Europe, and good morning, America. I'm Caroline Martens, and I'm working as a business development manager at ICsense, and I will be your host of this webinar. So welcome to our second edition of our webinar series to give you useful insights in how and when to use ASICs for different markets. The first session was held in April and covered several technical aspects of battery management ICs and functional safety aspects. But today we will focus on more business-related issues to take into account for considering custom ASICs. For most companies, the use of discrete components is often the first approach to hit the market. However, at a certain moment in time, the question comes whether or not to integrate these components into your own ASIC. Today, my colleague Jeroen van Ham will discuss this topic in this second webinar. And some practicalities before to start the webinar. You can ask questions in the chat box on the right side. These are moderated so I can see them coming in. And at the end of the session, we will have a short question and answer session. So Jeroen, the floor is yours.
Thank you, Caroline. Welcome, everybody. Today, we're going to talk indeed about a transition that, well, many companies go through. Often a company starts with making discrete components, building a circuit around it, but they see that over time, they produce the same PCB over and over again. And then the moment comes to think about, making an own ASIC, an application-specific IC with the circuitry built in from your company to miniaturize things. I will use this example later on in the presentation. It's actually one of the PCBs we got in over the years and had a look at to miniaturize this. I will come back later to this, what happened to this and how we made a transition to an ASIC. What's important to know is that the market in general, the ASIC market, it's a growing market. It's expected to grow about 10% with an annual growth rate over the period 2018 to 2024. So it's certainly something that many companies are thinking of. Now, the question always comes, is my company big enough to do this? Is it for high volume applications, or are, let's say, a few 100,000 units or 10,000 units enough to think of an ASIC? My application is quite complex. Is it possible to translate towards an ASIC, and how can I start with this? There's a lot of questions. I lined, let's say, the most common questions up here in this slide. One of the things that always comes back is the cost of an ASIC, so that's something we will also cover. And especially when you're looking into state-of-the-art technologies, nanometer technologies, then the cost is indeed very high. But you will see that for, let's say, general analog mixed signal ASICs, this is often not the case, and a business case can be more easily made in these nodes. First question, is it something for you? To be sure about this, you first have to position yourself on where you are. You have actually a few possibilities to make circuits. The first one is using standard ICs, commercial off-the-shelf components like ADCs, voltage regulators, etc., and make a breadboard, make a PCB out of it. The second option is by using an ASSP, an application-specific standard product. Typically, this is able to support multiple types of sensors and physical interfaces, can be capacitive sensors or resistive. The good thing is that it's a very flexible platform for small to medium volumes. Now, it's not cost optimized. You will use, let's say, 20% of the functionality of an ASSP, so it's not optimized for mass production and for large volumes. Also, you are a bit dependent on the specific manufacturer, and sometimes manufacturers, they decide to stop a certain production line, so there's always the risk of obsolescence. And that's the moment when you start looking into an ASIC. It's designed for one specific sensor, potentially portable between customers, but it's definitely a fit to one specific type of physical interface, also optimized for cost. If you look at just an ASIC as such, there's no competitive advantage unless it's made only for you. And of course, there's some NRE involved. So basically, the most exclusive way of doing things is having an ASIC only made for you with your company name on, your part number. It's the best fit to your sensor, unit cost optimized. Of course, there's NRE involved, but you have a competitive edge. It's very hard to copy this design. If you look at the typical reasons, and you should look at the list and maybe type off a few options. If you have a lot of options tapped off, it means that definitely this is something for you. What we see a lot is that people want to go to a smaller form factor, smaller size, together with a cost reduction, so reduction of the bill of material. The last, let's say, 5 to 10 years, IP protection becomes more important. A PCB is much easier to copy than an ASIC. So protecting your IP becomes definitely one of the key criteria to go to an ASIC. And then, of course, the benefits in terms of performance, like lower power, higher accuracy. There's also the level of urgency. Of course, some products you can never make without an ASIC. Think of a brain implant or a cochlear implant. It needs to be extremely small. You cannot do it with a standard PCB. So there's really a must to go to an ASIC. For many customers, maybe 80% of them, it's a nice to have. So you have a product, you can go to the market, but it's a way to optimize cost and to improve performance. And also the last one happens that if you do the calculation with NRE, with unit price, that you see there's just no business case to proceed. So there's also a possible outcome. Let's take a look at, for example, a sensor company wanting to integrate their sensor together with an ASIC. Typically, you can co-package both devices for better performance. For user convenience, you would do also some data processing inside the chip, inside the package to unload the main processor. One of the main things and the main specialties is to make sure that you capture the non-idealities. Every sensor has some non-idealities. In the end, you want to have a physical parameter going in and a digital word out. So you need to do some compensation, like offset compensation, gain compensation. There's always a dependency on temperature, for example. Well, this is taken care of in the architecture. And then the next, let's say, question pops up. How far do you go in integrating the digital functionality in your ASIC? It's a very important question because you can make an analog ASIC focusing on the readout chain and take the digital as a separate chip. That gives you a lot of flexibility, an external microprocessor to do all the calculations. But of course, if you go to the other extreme and integrate everything inside the ASIC with also a custom algorithm for your sensor, there's definitely an economic benefit of doing so. Here you see the whole spectrum of what is possible. In between, you can even choose for a system in package where you have an analog ASIC taking care of the sensor signal, the amplification, the A to D conversion, and inside the package you have an MCU taking care of the processing of the data and the compensation. You can integrate a microprocessor on site the ASIC. That's also a possibility. So there's a lot of pro and cons for the different options. So it's worth investigating those. We can certainly help you with this, and it's an important thing to consider. There's a checklist that you should complete before going into an actual development. The first is looking at your volume projection. Of course, this is the basis to make a decision whether you have a high enough volume to go for an ASIC. So it should be realistic. It should be a realistic overview of what you expect to be, where you expect to be in 5 years from now. Also, it's good to have your principle proven already on PCB or on breadboard before you step into an ASIC development. The business case, we can give you quite early in the cycle a view on the NRE investment that you will need and also the payback period. So those are important elements. Is the NRE secured for the development track? The first step, of course, is to come to a prototype, but you have to think of all the steps that follow, like qualification, like ATE support, going to mass production. That's also important. So always ask for a complete plan up to start of production. Having sufficient data on the sensor is also extremely important. We spoke already about the parasitics, the non-idealities, and this is very important data to start a study before you can really pin down all the specifications of the ASIC. Other things pop up, like a bill of material analysis to be performed, knowing what components should be left outside the ASIC and what to integrate. Stakeholders are informed at every aspect in which stage. And of course, somebody needs to support the development at your company. There needs to be a contact person who can answer questions about the system, especially in the first phase. Okay, before going into the actual process, the different steps, a very short word about ICsense. We are the largest fab independent European design company. We have about 80 full-time people, analog team, digital team working here. And we help companies making their ASIC. Either we do that in the design service mode, where we help the teams in the company to make the ASIC, or we can do it in a full turnkey model where we do the development of the ASIC and then afterwards take care of the supply, including qualification and ATE testing. So ICsense is also certified for medical developments, ISO 13485. We work a lot in the medical market, and we work a lot in functional safety developments. So our full development process is compliant to ISO 26262. Design headquarters are in Leuven, founded 15 years ago, and we are an independent subsidiary of the TDK group. If you look at the markets and some typical products we have developed the last 15 years, you see that it's very diverse over the markets, automotive, medical, a lot of industrial developments, consumer, and aerospace. Okay, let's get started. So first of all, before you step into a development, you'll want to know, do I have a business case? Is it worth going into the spot? So this is the first step to consider, doing an evaluation of the business case. Now, the problem is that at this point, you don't have all the specifics, all the requirements of the ASIC yet. So you need to make some assumptions. One important assumption to make is, what process will I make the ASIC in? Of course, there's a big difference if you look at a pure digital ASIC, where you have a lot of digital content, a high gate count, that you'll want to do in a state-of-the-art process node. But if you have mainly analog design, a sensor interfacing design with less digital content, you'll want to go to a more older technology. Typically, what we see is most analog mixed signal developments are in a 0.18, 0.35 nowadays, which is still a good compromise between analog and digital. The second parameter is the maximum voltage. If you're working in a pure consumer application, typically it will be 1.8 or 3.3 volt. But if you're working for automotive, you can have spikes, ISO pulses, EMC pulses that can go easily above 100 volt. Important to consider, because the amount of technologies that are available in these nodes is more limited. Wafer sourcing, this becomes a key parameter once you go into the high volume markets like the mobile phone business. There you'll want to have multiple wafer sources. And then of course we have process longevity. How long will the product be supplied? How long should the fab supply the wafers to you? And then again, the focus of the fab, is it a more digital oriented fab or really a fab that has a lot of experience with analog design? So the selection of this technology, the selection of the fab, is a very first important step to make up the unit price, to make a decision on where you want to play and what the total aspect of the business case will be. You step into the actual specification phase. This is the first step, and in my opinion, one of the most important steps, because there you will really define what the ASIC will do exactly. A lot of people ask us, why is this specification phase needed? I found a very nice cartoon about this. showing why it is needed. What's in the head of our customers, what's in the head of a system architect can be totally different. So you need to put it down on paper, you need to discuss about it, and this takes time. Okay, so what do we do in the specification phase? Well, basically it's putting together the puzzle and seeing what do we need in every phase. If you look at the different building blocks, the goal of this first phase is really to drill down into the details and specifics of every building block. You can say, well, I need a 14-bit ADC, but that's not sufficient. We need to know what is the speed, what is the effective number of bits, what is the INL, DNL. So all the details of this ADC, we need to put down in paper. Because once you start designing with a full design team of 10 to 12 people, it's too late to answer all these questions. You need to answer them upfront, because that's also the way to get the exact unit pricing before you start a full development. So this phase, this first specification phase, is the most important one. You really build the ASIC architecture, you choose a process, the technology partners, and you can line up a detailed NRE program, detailed timing, milestone program, and unit price. Typically 2 to 5 months, on average 3 months, and the most important here is a very clear communication between the design house and the customer. Of course, you will never start from scratch. There's always a lot of silicon-proven topologies available. When we do analog front ends, for example, we will work on the experience from the past. Same for ADC, same for digital architectures, power management. And this will help, especially if you look at these front-end circuits and you need to select a certain ADC architecture. We need to decide quickly what to do. You cannot spend 5 months alone on finding the right ADC architecture. That's not a goal. So we will reuse this silicon-proven topologies and then step into the actual development. This is the bulk of the project. Typically, a development takes between 11-15 months, taking into account one iteration. And this is, let's say, the most intensive part. You will work with a big team during this phase. The actual specifications will be put into life, into the actual silicon, and it will, in the end, bring you the prototypes. One thing that's important to consider is, how do we produce these? You can use a full mask set. In some cases we do. Anyhow, you need a full mask set to go to production. But the more economic solution is to use an MLM, a multi-layer mask set, where instead of having for every metal layer, for example, one mask, you put 4 of these on one mask. So you have 1/4 of the total amount of masks. But the good thing is you have a lot of flexibility. You can choose a tape out date. You can do metal updates. If you go to more state-of-the-art technologies where everything becomes a lot more expensive, people typically use for an MPW, also called a shuttle run, where you have to step in, and the shuttle runs for, depending on the technology node, maybe 6 or 10 times a year. So your flexibility is limited, but it's a cheaper option. But we don't recommend it, let's say, for typical 0.18 or 0.35 technologies. Packaging, also important. You can stick with the standard packaging like QFNs, TSSOPs, or you can go to more complex ways of packaging. So here's a good example of a device we made where you have 2 ASICs with on top sensors. We have 2 times the die inside the package for redundancy, to be compliant to ISO 26262 for automotive. And we even have capacitors inside the molded frame to take care of the EMC pulses. Of course, the design of such a specific package, custom package, takes a bit more time. That's also taken part of the actual development chain. It depends on the end product. Another option is, of course, to just have bare dies. We see this a lot in the medical area where you don't have a lot of space for implantable electronics, and you put the die directly on the board in a wafer level chip scale format. When we have the silicon back, the moment is there to test it. And it's really a parallel process. In the end, we send the prototypes to you so you can test them in your application, but we also test them specifically in the lab. And our focus is to really look at the different circuits on the ASIC, like the ADC, like the power management, to see whether it behaves as we expect. Now, we don't wait with verifying if the circuits are okay until we have the silicon. Before we send the silicon to the fab, we do a lot of simulations. We use standard tools for that. We scan over the full process corners. All the temperature, voltage variations are checked, all the combinations that are possible. We do Monte Carlo simulations. So that's very important to optimize, in the end, the chances of success. Of course, you cannot test every single device by hand. So in parallel with this bench testing, we also develop what we call an ATE program, automated test equipment program, and hardware to be able to test the device in mass production. Once we have these samples, once we are happy with the results of the silicon, we take a next step going to qualification and finally to supply. Qualification, of course, is needed to make sure that when the device is in the field, you have a sufficiently high reliability. Often you see this bathtub curve, where the blue line is the sum of all the failure mechanisms. The gray line are what we call constant random failures. They're in every die. You cannot avoid them. They're inherent to the silicon. You have the wear-out failures. By time, you will have more failures. But you also have what we call infant mortality failures, early failures. By doing a qualification, we can actually speed up this lifetime curve. So at the back, you see the curve, which goes over 10, 15 years. But by increasing the temperature, by increasing the humidity, we can speed up the process and we can simulate the actual behavior of the die in the field. That's what we do with qualification. Now, there are limits to qualification. For example, if you look at a typical ASIC 100 qualification for automotive, you have a limited amount of samples. So theoretically, what you can achieve is basically you can show that you have maximally 10,000 ppm. Now, often in automotive, this is not sufficient. So you need to go to much lower ppm numbers. And that's where specific techniques like functional safety come into play. I will not say a lot about it because our last webinar talked about this, but I do want to say two things. First of all, functional safety, the general, let's say, standard, the generic standard is this one, IEC 61508, which is applicable to mostly industrial developments. Automotive has also a functional safety standard, which is called ISO 26262. And you will see, if you look at the different ratings, they both have 4 levels, but they're not one-on-one comparable. SIL 4 is the most heaviest, the most difficult to reach, and for automotive, it's ASIL D. Our developments for automotive are typically at ASIC level, ASIL B, and by putting 2 ASICs together in a package or on the PCB, you can go up to ASIL D. You can work at different levels for functional safety. What's important is, if you look purely at the ASIC, at the die, we add diagnostics. We check the output of a band gap, the output of a voltage regulator to make sure that everything is as expected. And that way, by adding these diagnostics, we can make sure that no unexpected things happen while the device is in the field. You can also work at the next level, which is the package level, by combining multiple dies inside one package and really have a full redundant channel. And then finally, the last level is that you have on your PCB different ASICs combining, and then at, for example, the engine control unit, the ECU level, you can check if the output of both ASICs is the same. Just to give you one example on this, here you see a picture of 2 ASICs being put on top of each other, giving you normally the same output. If you look at ppm levels that you can reach with that, it's quite impressive. Typically, we work towards ppm levels below 1 ppm for high reliability automotive applications like airbag sensors and things like that. But obviously, and that's, I think, clear now, so you cannot do that alone with qualification. You need more. Okay, so now the design is finished. Of course, the business case, that's where it's all about. So let's have a look at how to calculate such a business case. Typically, there are a few questions to answer. The first thing you want to know is what's the volume of your product? Secondly, what's the project timing? When will I be on the market? Then the NRE, and finally, what will be the unit price of the ASIC? We can't help you with predicting the volume. That's up to you, but we can help you with the lower three ones. So looking at project timing, NRE, and unit price. Looking at unit price, it's always a drill down of specific parameters. You have the silicon cost, you have the cost of assembly, so the package itself, but also putting the die inside the package, bonding it. The test cost, of course. You have the specifics to go to very low ppm targets. You have the maintenance of the test equipment, and then finally you have everything related to logistics, shipping the dies, ensuring the wafers, ensuring the ASICs during transportation. You can drill down to different levels, and what you see is that there's a lot of parameters that finally determine the unit cost. So it's impossible to say in the beginning what will be the unit cost. You have to make a lot of assumptions. Throughout the process, everything will become more clear, and you can really pin down the exact unit cost. What we do in the beginning of a project in this business case evaluation is make assumptions based on past projects, but also on a specific architecture. We can estimate quite well the test costs, the silicon costs, the total area of the circuit. So that's something we can help you with in an early stage. If I look at a typical unit prices, well, in the last 15 years, I've seen ASICs of 10 cents, 10 euro cents, but I also have seen ASICs up to a few euro. So it really depends on the specifics. That's something we can help you with, but again, the volume is also a very important parameter, and that's something which is up to you. This is a total NRE investment for a typical project from kickoff to start of production. You see that almost half of this pie is going to study, design, and layout for the first cycle of the development. So that's a big portion, and that's really the reason, of course. You can do things quick and dirty, but in the end, your respin will be longer, or you can even have more respins. So the effort you put here is extremely important. And it's important to take also the time to do this right. Our goal is always to reach mass production silicon in the first run. We need typically 1, maximum 2 cycles to come to this result. And I've seen a very nice picture passing by a while ago saying there will always be someone who says they can do it cheaper. In the end, you need to take realistic assumptions. In analog design, especially, you trust on the models of the fab. You cannot predict anything, so you need to take into account in the global planning 2 cycles, 1 design cycle and 1 redesign cycle to tweak the results of the first silicon. That's very important. People will always convince you that it's possible to have a first time right. Well, it is possible to have a first working prototype, functional silicon, but to come to the mass production version, we always take this extra cycle into account, just for safety. Looking at the third aspect is the timing. There it really depends on the market. I've looked at the tape outs we have done over the last 15 years. It's about 130, and split them over the different markets. And you see there's a huge difference between a consumer product and a medical product. Typically in consumer, you can go from kickoff up to start of production in 1.5, maximally 2 years. Industrial, it's a bit longer, not that much. Automotive, already you're adding quite a bit, because typically the safety aspects are much more important. And then you have medical, and the big question mark with medical is always the last stage, the qualification, the FDA approval, the patient testing. This takes time. And well, a nice sentence I also read recently is, well, the bitterness of poor quality remains very long after the sweetness of achieving the deadline is forgotten. So take your time, make sure you have specified and defined the milestones very carefully together with your design house of your choice. Some practical examples, some real world examples. The first one is actually a development we've done about 5 years ago for automotive diagnostics. And remember the PCB I showed you in the beginning of the presentation. I repeated it here. So it's actually a PCB with quite some relays on there, which was targeted to work in an diagnostics handheld device in a car, where basically the goal was to miniaturize this circuit, to put it into a smaller device. We could integrate almost 20% of the devices here. Some components are not worth to integrate. For example, caps of several microfarads. You cannot integrate them on an ASIC. It would not be a very wise use of silicon area. In the end, you see also quite a lot of relays, which we replaced by a pin switch matrix, a high voltage pin switch matrix, implementing a lot of automotive protocols also on this device. One of the key challenges is when you make a relay, when you integrate a relay on CMOS, to have very low RDS(on). And that's what you see here. Even with the bare die, you can see the switches on the circuit. The choice of technology was also very important in this project because the customer mentioned that there will be ISO pulses in the car going up to 150 volts. So we selected here a silicon on insulator process up to 200 volts, high voltage. So if you compare what the typical PCB implementation costed with off-the-shelf components, you have a curve like this. So using standard relays, standard components, going to the actual implementation of an ASIC, this is the curve where you see there's an initial investment, but also a payback time after 2.4 years. So after this period, you start saving money every year, year after year, and you have a very small device. So in the end, the customer could fit this device into an end module, which was about 1/5 of the original volume. A second example I want to show you is in a totally different industry. It's for temperature and oxygen measurement in molten steel. When you want to measure the oxygen level and the temperature in molten steel, you need very precise sensors. And the way this customer used to do it was with a data logger unit, custom made, and shielded cables, coax cables connected to various sensors, oxygen and temperature sensors. Now, of course, it was a bulky unit, a very expensive unit, because you can imagine if you put these cables into the molten steel, they will melt. Of course, there's a casing around the sensors to make sure that you have a certain delay and be able to measure this oxygen and temperature level. But you always burn the complete system at the left-hand side. The volumes were quite big. We were talking about 100K, 200K units a year of these cables. So definitely the driver of the project was to do a cost optimization, to increase the performance, to have actually the sensors closer to the readout electronics, and to reduce in general the size of the system. So what we did, we translated the system to a QFN-based device, an ASIC, where we have the sensors literally 1 centimeter apart from the ASIC, put on a small PCB, and we can communicate with these ASICs over cheap copper wires. We send over the data and we send over the power over these wires. So this was done in a 0.35 technology. Why? Because actually the digital content on itself was not dominating. We had 16-bit delta sigma ADC resolution. And most important spec here is, if you want to do precise measurements, we needed to have a microvolt absolute accuracy on the measurement of the temperature and of the oxygen. Some takeaways. First of all, it's very important to think about the total development and the total development time. You cannot make an ASIC in 5 months. People might want to tell you this, but it's simply impossible because you're not looking at an ideal situation. One thing is to meet specifications of the ASIC in an ideal setting. That's one thing, but of course, nothing is ideal. Sensors are not ideal. The environment is not ideal. You have temperature variations, voltage variations. There's no single supply, which has no ripple. So there's a lot of non-idealities, and everything has to be simulated to be sure that the system will work in a real life environment. Also, the addition of diagnostics becomes important in industrial or automotive environments, and this adds an extra layer of complexity. And then finally, you have all the documentation. If you want to pick up the design in 5 years from now, or if you need to pass audits or FDA approval, you need a very firm documentation showing that you have done everything to optimize the design and to make sure that nothing will happen in the field. The second thing is, or myth, is that ASICs are only for high volume applications, which is also not true. Especially if you look at medical applications, we see that actually the volumes can be very low because, well, it is the only way to go to the market. But also for industrial, you don't need to have millions of units every year to have a business case. So don't hesitate to let us know, to send us your first requirement, and we can very easily give you a first indication of what the NRE cost will be, what the unit price will be, and what the length of a development will be. It's always a balance between, at the one hand, the product lifetime. Maybe you have a product running for 10 years, but it's totally different than if you have a product running for only 2 or 3 years. Your market share, volume, confidence in the growth strategy. When you have an ASIC, you have a competitive advantage, a small solution. So you will have growth. And then finally, amortization of the NRE over the units. You should look at the total cumulative volume of the ASICs to justify the initial investment. So summary, ASIC development becomes more popular. We see a growth rate of about 10%. It's always very important to choose the best fit for your product. In some cases, well, it's just not worth going to an ASIC. It's best to stay at a component level. Then finally, the business case, that should be leading. Don't judge only on a volume. Really make the full business case. And then finally, analog and digital ASIC designs are totally different worlds, especially in the selection of the technology. Those are different things. For an analog or mixed signal ASIC, you do not need a state-of-the-art technology of 40 nanometer. It's much better to go to 0.18 or 0.35. Challenge your supplier technically, ask them a lot of questions. Before you step into an actual development, make sure that you have the confidence that it will be brought to a successful ending. And then finally, when something looks too good to be true, when you get a promise to have the ASIC within 1 year in production, well, be very reluctant, ask a lot of extra questions, because we have never seen ASICs going to the market in less than 1 year, when you take into account all the quality aspects that are needed. So if you have any questions, I see there's already some questions coming in. You can always ask some questions in the chat box. We will try to answer a few. So I will give the word to Caroline.
Indeed, thank you, Jeroen, for the interesting presentation. Perhaps one question. So when we are having a discussion with potential customers, we always hear that the customer is considering to integrate their current PCB solution into an ASIC, but they have no experience or they have no spec available. So what shall they do?
Well, this is indeed something that's a bit a chicken egg problem. You need to have a specification before you can make an accurate calculation. It's not needed to have a full-blown specification in the beginning. What is typically sufficient is to have a good block diagram, to have a description of, for example, the sensor and the specifics of the sensor, and to know what do you want to reach at system level. Based on that, we can already make a very good assumption on what a die size will be, what the complexity of a project will be. And we will start asking questions about the different parts of the system to make sure that we have a good feeling about the complexity. So it's not needed to have a full detailed specification in the first phase of a project. We will do this exercise actually together, because the first phase is a phase where we have every week at least a call to talk about the progress, to discuss the technical parts of the system. So it's not needed to have a specification. I've even worked on projects where we had only one sheet of paper with a block diagram on it. So that can be definitely a start for a discussion.
Okay, so we received a question from the audience. How much effort is added if you need a functional safety product, for example, for automotive or so?
That's a very good question. And well, of course, there's no fixed percentage that you can put on it. It also depends a lot on the level of functional safety. So in general, I would say that if you look at an ASIL-B development, which is today, let's say at ASIC level, a very common level, you should think of about 30 to 40% of adder just for implementing the diagnostics, the overhead of doing an FMEDA, of having all the discussions on safety, making sure that the test coverage is at the level you require. So there's a lot of extras. So purely looking at the design efforts, it would be an addition of 30 to 40%. ASIL C or D, that's a totally different story, because there the level of what you have to do is a lot higher, a lot more complex. It's very difficult to say, but if I look at the last development, it will probably be for sure about 50%. But that's something we can always look at based on what is needed, what the level of coverage should be.
Okay, so in your last slide, you also mentioned the importance of having a difference between first-time functional and first-time right designs. Perhaps can you explain a little bit what to expect and what the difference will be?
Yeah, so that's something that came back in one of the slides already. Functional, first-time functional, it's a term we often use. It's to say the first sample, the first prototype will be usable in a demonstrator, will be usable together with your device, and is perfectly suited, for example, for startups to show to the board of investors, to show that the product will become something. You always need this respin, or let's say in 90% of the cases, you need a respin to tune the yield, to make sure that in every single temperature or voltage corner that you reach the specification. So let's say the first is first time functional, a working prototype. First time right is something you also see sometimes, but that's something that, especially for analog design, you should be very careful of saying that, because unless it's an extremely easy design, it's very hard to make a commitment, because you trust on the models, you trust on the simulations to tape out.
Okay, so we have not received any further questions, so I think we can conclude this session for today. I would also like to advertise for our third session that will be organized in September. So we'll organize a third session on custom ASICs as an enabler for MedTech. That session will start or will go on September 24th, also at the same hour. So if you're interested, please feel free to register, and then we meet again.